else going on. So the only other thing right now that we learned is the binomial part. So when you do this, find your N, your P, your Q, and see if this in fact is a binomial distribution. So 35% success rate, 1 minus 65, and you randomly selected 500 workers. So this is binomial. The next thing you must do is test. You must test to see if you could use it. I realize you know it's going to work. Just give me a little check mark. Show me you made an attempt. The mean is your N times P. And now the standard deviation, you can find that as well. Now you're almost ready. So you write your probability statement. Exactly means x is equal to 175. But since 175 is this little piece right here, there's no area to that. I have no area in that. If I did a z-score for 175, where do I find the area? To the left or to the right? There's no area for it. So I make a bar. When it's in exactly, I drop the left side, 0.5. I raise the right side, which is the same number, 0.5. So all this did was give me a little bar in here. And that has got to be a pretty good probability. It's smack in the middle of your graph. It's a good chunk of work here. So find your pieces, subtract. Don't subtract your z-scores, subtract your areas. Okay, then it said use the same situation, no more than 225. So no more than means less than or equal to. You've got all your information, your U, your standard deviation, you already found that, you already tested it. So just correct this for continuity. If this is the highest, do this down. This makes the most sense. Raise the upper level 0.5. There's your new probability statement. This is what you're putting in here. It makes a slightly little difference. You can still do that part in the calculator as long as you corrected it. For those of you that like the calculator, you can still use the calculator and bypass the z-score. And the calculator works great for this guy. Just remember you have to correct it and you have to find your standard deviation and your mean. For a little problem, it has a lot of work because we weren't given a lot of information that we could use. We had to do something to all that information. Okay. From here, we have one more, and that was an at most. At most says that is the most. It's kind of like the no more than. I can't be more than, I can't be more than this either. This is the most. So again, 200 is my upper level. I increase that 0.5. And because my area is to the left, I don't have to subtract this out. Oh, let's talk about this for a second. This guy. Your z-score is way up here somewhere. You want the area to the left. Your chart goes up to 3.49. Anything else is kind of like negligible, they consider. So to the left, that area is 100%, approximately 100%. If it's to the right of it, then I'm approximately 0. Okay, not exactly, because 0 means never happen. And 100 means always happen. This is also pretty good probability that will happen. You good with these? Okay, somewhere here it is. 28, and I realized a lot of this was redundant, but the more you do them, the better you get at this. So, I see a statement here. I found that 51% of adults think high school students should be required to learn a foreign language. You randomly select 200 adults and you ask them yay, nay, and then with the response. So if you want to write your z-score, you have no mean. Again, you have no standard deviation. So this leads us to believe this must be a binomial situation. So just make sure that you check and that it is a binomial, and then you test. You almost have to do the first test anyway to find u. So at least if you do that. And if you just check the smaller one, I'm okay with that. Find your standard deviation. When you make your graph, again, if you want to estimate, you guys are to the point now where you can start just estimating. Estimate your mean at 102. Estimate your standard deviation at 7. This makes life a little bit easier to do your chart because you're going to just change your z-score anyway because you're adding your 0.5 or subtracting your 0.5. So you're still in the ballpark. You're still wherever you need to. It just makes it easier to subtract and add this way. Yeah, if I could. Whatever this is. And whatever. So do it with the 7. You don't have to worry about the decimal point. I do this so that you get a flavor of this. Thank you. And when you look at this and you're looking for 119, you can see where 119 falls, and you're looking to the right, you absolutely know that your area can't be very large. So when you look up that number and it's pretty big, 80%, 90%, you'll know to subtract it from 1. And you'll also know that your z-score has to be positive here, not negative. So the sketch still gives you reference. Doesn't have to be as detailed. In the beginning we kept it a little bit more detailed, but we kind of know what we're doing a little bit more. At most, don't forget to correct these for continuity. At most, this is the highest level. So add 0.5. At least this was the lowest one, subtract 0.5. That's what you're using here in your z-score formula. And if you use your calculator on this, I need to see what you put in, because this is what's going to happen. If you don't use the 0.5, the correction for continuity, and you use your calculator, I'm going to put in mine 0.5, and my calculator answer is not going to match yours. And so therefore you get it all wrong, because I didn't see what you put in. I don't know which way your correction went, or that you corrected at all. So if you use your calculator for this, make sure you show me what you put in there. I need to see your correction for continuity. And then the last part of this was between. Remember, a between is going to drop at 0.5 and raise at 0.5. Be careful on this guy, because the between says I'm somewhere between 80 and 120. Between 80 and 120 is here. It doesn't mean use 80 and 120. What word would I look for if it said use 80 and 120? Inclusive. So I'm only in between here. Drop this guy to 80.5. Raise this one to 119.5. And again, you can do it on your calculator. You can do the in-between on your calculator. I don't have a problem with that. Just make sure you show me, because I need to see that correction. Subtract your areas. Don't forget to subtract your areas. Don't subtract the z-scores. And don't subtract them from 1 first. Because there's always area to the left. So leave the z-scores and then subtract the areas. Questions so far? No? Okay. And the last one, this one was a little bit different. They took your scenario and they changed n so that you could see what happens to n when you do this. They kept increasing n. And this way we can see what actually happens to it. Between here and here. My n is increased and my n is increased again. So notice it changes your mean, it changes your standard deviation. So we're looking to see what's happening. Your statement stayed the same. You wanted to find the probability that each company will get at, the discount. To get the discount, they need to have at least 30 employees. So therefore, at least greater than or equal to 30. Probability that x is greater than or equal to 30. Again, you can use 30, 31, drop this to 29.5. You use the same probability statement all the way through. But what changed is your mean and your standard deviation all the way through. See, I can just move this down one little bit. Yep. And your mean and your standard deviation changed. So and we're greater than, so it's your area to the right, your 1 minus that. So you could see your z-scores changing here. Your z-score was really high, then it got closer to the middle, then it went into the negatives as we did this. So as you increase, your probability should get better. Probability went from almost about 0 to about 18% to almost 100%. Can you do this? Questions? The biggest part, guys, is like which one to use. Plus, I set your test up so I do 5.4 first, and then we switch to 5.5. You'll know when we switch to 5.5 because I'll ask you, can you use this as a test? And then as soon as you use your test, you'll know we're in 5.5. So this tells us the annual consumption for your population as a mean. This is your population mean. This was your population mean, and this was your population standard deviation. Here's your random samples. This is your N. So you have to find the mean and the standard error of the mean. Nick, you probably weren't here. Were you here for this? Oh, okay. Let me check and see. So again, this is how we'll start. We'll say, find the mean. The mean is the same. The mean for your sample is the same as the population mean. And find me the standard error of the mean. This is the same as your sample standard deviation. And here, this is the major change. We only use this for this one. Yes.
So I understand you only use
Yep. They talk about your population first. They give you the population mean. They talked about our population of all of the consumption of citrus fruit for your population. So they give you your population mean, and then they give you your population standard deviation. Now, from the whole population, they took many samples of 35, and they took their mean, and then they took the mean of all those samples. Like the thing we saw yesterday when he kept saying that too, the sampling distribution for the means. They take different sample size, but the same sample size, different samples from the population. It goes right back in the population again, and they take the average from those. Your mean for your sample will be the same exact as your mean for your population. And your standard deviation will be slightly smaller. That's the one that's going to change. And what does that mean? That means when you come down here to a problem, when I come down here to a problem, here's a typical problem. I have a mean for my land and buildings for farms in Illinois. So this is my population. There's my population mean. There's my population standard deviation. Sometimes they put it at the end. And they said a random sample of 36 is drawn. So my mean is the same. I calculate my new standard deviation. From here, I'll make my chart. And then I do each one of these. What's the probability that X was less than 7,200? So we can see 7,200 is about over here. That's a good chunk of it. So I use my formula. Do your calculation there, rather than take this one that you just calculated and rounded. I would just do it once at the end, not in between. You need to do it for your chart, but then do it in your thing. Area to the left, leave your area to the left. More than 6,500, you're not changing, you're not correcting anything. Yes? Not really, because just watch. Watch the difference between these. It says the mean value of your land per acre in Illinois is 6,700. Your standard deviation for your population is such and such. your random samples are drawn. What is the probability that? And we've got these. Now, here's the difference. Here's the other one. A survey found that 73% of blah, blah, blah. You randomly select 12. That's the only time this is in common. And you want to determine what your probability would be for such and such. If I go to use my Z formula, I have no mean. As soon as you say, oh, okay, here's my probability statement, whatever, this one's just a test, but what if they gave me a probability? Here's my probability, X is greater than, I don't care, whatever this happens to be. As soon as I do this, I say, okay, let me put this in. Whoops, I have no mean, I have no population mean, I have no standard deviation. So that says, step back a second, you must have a binomial situation. And this tells us binomial. Remember way back in chapter 4, there are 4 things that make a binomial distribution. 2 choices, that's your P and your Q, probability of yes, no. A fixed amount of times, your probability doesn't change, and your X is your random variable. So as long as I can identify those, I can use this part here. And I can make this approximate a normal curve. That's immediately how you tell. So in this guy, I am able to set my z-score up, aren't I? So I set my z-score up and I say, okay, z-score, what if I just started like this, right? So I say my X value is 7,200. My standard deviation is here. Oh, why did they bother giving me a random sample? What do I need to do with my random sample? So always start with, there's my mean, there's my standard deviation, there's my n. Well, if I do that, I didn't use my n, right? So where would I use my n for this? Right here. That's the difference. Make sense when you look at both, when you compare both? And this one, remember, this is the one they had to tell us it approximates a normal curve, or your sample size had to be greater than or equal to 30. So what's our sample size in this guy? 36. So therefore, we approximate a normal curve. How do I know in my binomial if I approximate a normal curve? If n times p is greater than or equal to 5, and n times q is greater than or equal to 5. I have to do a test for that. But here, I just do a test to see, is my population normally distributed? Then I'm good. Or, is n greater than or equal to 30? Then I'm good. So I'm actually still testing to see, am I in the ballpark here? Am I in the right ballpark? Let's put it that way. So, here was the difference. We found them. Once you get to here, everything else is pretty much the same. Just remember to divide by this. There's no correction for continuity here because this is continuous. Okay? Because can the value of your land have a decimal point? Can my land be worth $100.50? $100.22, say, per acre. Yeah, I could. So there's my continuous line. My discrete values, ooh, no. I'm counting the number of people. I can't have a partial person. Notice your binomial is different. You're asking people, yes or no. So only 5 people can say yes. 8 people can say no. But 8.2 people cannot say yes. See a difference here? Kind of? Alright, so this is what you're going to look at. And I'll kind of separate the test so that you can kind of see it when it's going to switch over. The between, and you want to do this on your calculator, you can absolutely do this in your calculator. Those of you that like the calculator, second theirs, put this in on an in-between. There's your lower limit. There's your upper limit. Your mean. Your standard deviation, put it in and let your calculator do the divide. Just put it in here and your calculator will divide. If you want to say by 6, that's fine. And then paste. You can bypass all of that if you like to. But if you use your calculator, you need to tell me, use the calculator. And give me the steps that you put in. This one's pretty straightforward, but I won't see your standard deviation in here. So if you forgot to divide by your square root, your answer is not going to match my calculator answer. And you're not going to get any credit at all versus just lose a point because you forgot to divide by the square root. Know what I'm saying? Okay. So that's the difference between these. Here we switch to, and this is exactly how I'll switch on yours. We just spent a lot of time with this guy, so I'm not gonna do these again. You can find your pieces. Are we okay with this part of it? Okay, let's take, okay. So the first one says, for 9 and 10, we're using the same mean and the same standard deviation. We're dealing with the population. A random sample of 60 people is selected from this population. Oops. From this population. What is the probability that the mean IQ score of the sample is greater than 105? Okay, we gave you that, right? Then I asked you down here, well, let's do this one. Your mean, what is your mean for your population? So what is your mean for your sample? 100. This is what's going to change. We're going to do 15 over the square root of 60. What did that come out to be? You have it on your papers. This is what you handed in. 1.94. Thank you. Now, probability that it's greater than 105. So, here's your z-score. We're doing a test of your sample means. So, what's your z? 2.51? 2.58. Thank you. Now, you're looking up your area to the right. So, should it be a large amount, your final answer?
No.
Your final answer? No. When you first look it up, yes, and then we're going to have to do what? Subtract it from 1. So, you're going to subtract your area. And what's your final answer? 0745? No? What'd you get? Oh, 049. Very small. Okay. Now it says you randomly select one person with an IQ greater than 105. Or are you more likely to randomly select a sample of 15 people with the mean score greater than 105? So, how do I know which one is the population, and how do I know which one is the sample? Because I'm selecting what? One person from my population, right? Which is kind of hard to get this one person that's greater than 105. So I still say x is greater than 105. Okay, almost the same thing that I had to say here, greater than 105, but I'm one person. So this comes from this. No sample. This is my population. So what's this z-score? What's it?
130.
I hear it from 5 people here.
It's 130. So it's 0.333.
0.333. Okay. So now, when I look up this probability, it's to the right. So I'm already to the positive side. I still have to subtract it from 1. What's the probability? Is it going to be less than 50% or more than 50%? Visualize your graph. No, after I subtract it from 1. It will be here. There's my half cutoff. It will be here, right next to it. It will be slightly less than 50%, right? So what's my area? Point 3707. Thank you. Now, here's my sample. I have a sample of how many? My probability statement is going to stay the same, basically. It's just my sample means. But that's kind of like, doesn't matter to me. I still do this. But now what do I divide by?
Square root.
15 divided by the square root of 15. This is the difference. So now what's my z-score? Okay, I'm going to divide by a smaller number, so I should get more, right? All right, I still look up the area to the right. So now, if you think about it, 1.29 is like over here. Isn't this area less? So what's my area to the right? 0945? 85, thank you. So, this has about a 10% chance of happening. This has about a 37% chance of happening. In this case, who has the better chance? The population. Usually it's the sample, but it depends which side of the fence you're on. Okay, so know how to do that. We good? We spent a lot of time doing these.